So let's get back to these shear and moment diagrams. If we want to draw a diagram that tells the shear at every single point, that's our shear diagram. If we want to know the moment at any point along these simple beams, then we can draw our shear and moment diagram. We could cut it at lots of different places and resolve some of the forces in y equals 0, some of the moments equal 0. But we're not going to want to do that. We're just going to want to look at the loading and then ask ourselves, okay, what does that loading do to my shear diagram? And what does the shear diagram do to the moment diagram? All right, so we already kind of mentioned that we're kind of integrating if we're going from loading to shear, from shear to moment, we're integrating it, or vice versa, we're taking a derivative if we're taking the moment, take its derivative to get the V, take its derivative to get back to the loading. So that's kind of what this last page right here says. So we know that a change in my shear diagram, that there are two things that will change my shear diagram. An external force, right? If I just have a force drawn on my loading, it pushes my shear diagram up or down by the magnitude of that force. Let's go back to see that. Let's go back to see that. So two things, I'm about to write another thing that changes the shear diagram. But the one thing, I think the easiest thing is a force just immediately pushes it up or down the same direction. All right, well, let's go back to the one that we did right here. Okay, you see that 100-pound force? That immediately pushed my shear diagram straight up by 100. You see that 250? It pushed it down by 250. So I was at 100. It gets pushed down 250. So now I'm at negative 150. And then I'm going, and then I get pushed up by 150. So I'll walk back. Now I'm back to 0. So you see how just forces just immediately push the shear diagram up and down. Also, distributed loads, they don't push my shear diagram up and down immediately, right? It pushes it down over a length. So let's go back, and we're going to have time to walk around. I'm going to get y'all to walk around and look at these. But do you see that distributed loads like this, it pushes it down, not immediately, but it pushes it down. Let's see if we've got, yeah, look at that one. You see how it pushes down my shear diagram. I think the shear diagram is easiest to draw. The forces push your shear diagram up or down. If it's direct, if it's a force, at one point, it immediately pushes it up. If it's a distributed load, it pushes it up and down gradually. Okay? Pushes it up and down gradually. Do you see how a uniform pushes it down uniformly with a slope of negative 20, right? In this case, if that uniform distributed load is a uniform 20, then my slope is a uniform downward 20 of my shear diagram. Okay, so those are the two things. So distributed loads, and think about the area under distributed load. Right, we already know from statics that the area of the distributed load is equal to the force. So the area of that distributed load, that's how much it's going to get pushed down. And then you just have to ask, okay, does it get pushed down linearly, or does it get pushed down steeper on one side than the other? For instance, this one, it's not getting pushed down too hard right here, but it really starts getting pushed down. Doesn't that make sense? I think right there. And it's also due to the fact of the slope of V is the loading. Okay, so the shear diagram changes due to areas under distributed loads or external forces. Similarly, the moment gets pushed down due to external moments, right? If there's a moment drawn on there, then my moment diagram immediately goes up or down. Okay. Or the area under the shear diagram. The area under the shear diagram pushes my moment diagram up or down. Let's go back and see. Let's try to see if we can find some external moments that immediately push my moment diagram up or down. That one right there, that 40 right there, immediately pushes it up 40. We'll talk about whether clockwise or counterclockwise is up or down, but I think we can see right clockwise is going to push it up. So here it's the area under the V is what's pushing my moment diagram up. This right here would be a positive area if it's above the axis. That would be a positive area, so that's why it pushes this M up right there. This would be a negative area, that's why it starts pushing it down. Okay. All right, so that's kind of what I'm looking for when I'm drawing my V diagram. That's what I'm looking for when I'm drawing my M diagram. And then two other things to know. Loading is the slope of V, and shear, V, is the slope of M. V is the slope of M. Okay, so if we can maybe I could color code this. When I'm drawing my shear diagram, I'm looking for these three things. External forces, push it straight up and down. Distributed loads, push it up and down over a length. And knowing that the loading is the slope of my shear. And then when I'm drawing my M diagram, I'm looking for external moments that push my M diagram up and down immediately. I'm looking for the area under the shear, which brings it up and down gradually. And I'm thinking, okay, V is the slope of M. V is the slope of M. Okay. All right, so that's a good page in our notes. So kind of, what am I thinking when I'm drawing my shear diagram? What am I thinking when I'm drawing my moment diagram? Now, you could go back to, I don't really like to do this, and I'm not really going to teach much of this. You could write an equation for your shear. You could write an equation for your moment and know that they're the integrals, they're the derivatives of each other. But you would just have to do that for every section of your beam. So anytime something changes, you need to write a new equation for this section, a new equation for this section. You have an equation for each section. So I think that's more work than just graphically doing it. That's something to fall back on. There's one problem, or sometimes there are problems where you might need to write an equation. Maybe if you want to see when it passes through zero, sometimes it's easier to write equations for those as opposed to our graphical method. But I'm just going to use our graphical method, and so I'm going to be thinking these three things when I'm drawing my shear, these three things when I'm drawing my moment. Okay. All right, next page. I don't think this is a good way to say it. Let's look at the end of each of our shear and moment diagrams. All right, let's look at the end of the shear and moment diagrams. And I like to think about it like I am walking along this shear and moment diagram. So I'm about to hop on the shear and moment diagram. And so I like to think of it as starting at 0, right? I'm off the beam. There's obviously 0 shear off the beam. So I start at 0, and immediately whatever you need to solve for the reactions, the supports. And so if right here on the very far left side of my beam, I immediately have a 150, then it takes me straight up to 150. And then I'm walking along here. There are probably other things through here, distributed loads, things like that bring me back and forth. Now, I need to get off the beam. All right, I'm walking along this shear diagram. I need to get off at 0. So just make sure that the last thing on your beam takes you back to 0. Okay? So you start at 0, and just make sure that the last thing on your beam, it ought to, and it's a good way to double check that you're correct, it ought to take you back to 0. So this one was right here, and then it took me up to 0. So this one, depending on what was in between there, just make sure you start at 0 and you end at 0. Right? You start at 0, and something might immediately happen, and then you end at 0. Now, this moment, if we're looking at this beam, if there is no moment right there, then it starts at 0, and then there's no moment right here. It's going to end at 0. I mean, maybe it goes up, down, around, in between there. So just make sure you start and end at 0. And I say you start at 0, but you might immediately, do something. You might immediately do something at the beginning and the end. Okay, let's look at this one. What if you had this is probably a wall right here. Remember, at walls, at fixed supports, you might have a moment right there. So let's say we're at a wall, and we've got a we've got a force and a moment. What would the V look like? The V would immediately go up to 20. I'm not sure what's in between here. I better end right here at -10, so that the last thing that happens is it brings me back to 0. Now the moment right here, and we could, cut it, and I don't have this sheet in our notes. We could cut it and see what a clockwise moment does to our moment diagram, or we can cut it and see what a counterclockwise. But a clockwise pushes it up. So this one would immediately go up to 75. Not sure what else happens, but I know I've got to end at 0. Okay, so that was a rough page, but the main thing, there's probably something immediate that happens right at the very beginning. And then at the very end, make sure you end at 0. Make sure you end at 0. Okay. So let's look at this. We're trying to draw our shear diagram. So I just want us to look and see, okay, when I see a force, what does that do to my shear diagram? When I see a uniform distributed load, what does that look like for shear? When I see a linear distributed load, what does that look like? All right. A concentrated external force it just immediately drops at whatever value that force is. So it's almost like, I like to think of it as if I'm walking along, and then that force pushes me down by that magnitude. Okay, what if I encounter a uniform distributed load? Let's say I start right here. This pushes me down. Where do I end up? Let's see, the change from beginning to end would be the area under the loading, right? The change from beginning to end would be the area, right? Because it's like I just replaced this with one force. So base times height would give me how far I go down from beginning to end. And now I just need to ask myself, is it like this? Is it like this? Is it like this? What kind of shape am I going? So I'm thinking that the slope of the load pushes me down. So this is a uniform, it's pushing me down uniformly, right? A uniform distributed load pushes me down in a linear fashion. Okay, how about this next one? How about we're going from one magnitude to another magnitude? If I started at whatever point I start at, I'm walking along here, so I'm starting here and I encounter this distributed load. Well, I know that I'm from here to here, it would push me down the area under the loading. So whatever that area is, it's trapezoid. You can think of that as a triangle on top of a rectangle. But now, do I go, is it linear like the other one? Does it go like that? Does it go like that? Ask myself, or tell myself, the loading is a slope. So it's pushing me down some on that side, but it's pushing me down even harder on the other side. So do you see it would be kind of like that curvature, right? That curvature. And so not only am I looking for, okay, did you get that point right and that point right? I'm also looking for, did you get the curvature correct on your shear diagram? Okay, but the main thing is the loading pushes me up or down. The loading pushes me up or down. All right, the moment. A clockwise moment immediately pushes me straight up. So if I was down here, it's almost like I'm walking along this moment diagram. Clockwise moments immediately go straight up by the magnitude of the moment. All right, that makes sense. All right, what if my V diagram looked horizontal? What if my V diagram looked horizontal? Maybe I started right here. The change in M is the area under the V diagram. So that area, and it's above the axis, so that's a positive area. And so it would go from here to whatever value that positive area is. Then I would ask myself, okay, does it go straight that way, that way? So the other thing I'm asking myself is, or telling myself, V is the slope of M. V is the slope of M. So if this value is 10, 10, 10, 10, it has a slope of 10. That would be a straight line from beginning to end. Okay. If V is linear, the change in M is still the area under V, but then the slope, remember, V is the slope of M. So, sorry, I'd find that area, and that would tell me how much my M diagram changes. And then V is the slope of M. So let's see if this makes sense. Let's say this starts at 10 and it goes to 15. Okay, I had a positive slope of 10, but then I had an even steeper positive slope of 15. This would be more along that type of curvature. So V is the slope of M. Okay. And then if you have, not really exponential, but like an x squared, if this is like an x squared, then this would be a more drastic x cubed. When you get into these, then yeah, it might be helpful to have an equation for that x squared moment or shear diagram, and then you can take the integral to see something x cubed, because we'll talk a little bit about it, but finding the area under an x squared, sometimes we can do, not too bad, but sometimes it's difficult to find the area under that curve. Okay, and then a few more things before we try some. When V crosses 0, when your shear diagram crosses 0, then that means the V is the slope of M. That means my slope of my moment diagram was 0. It was positive, positive, positive. Then it became 0. Then it became negative. So, it might look like this, where V crosses 0 is a max or minimum of the moment diagram. Correct, right? When V crosses 0, then my moment diagram is at the maximum or minimum. All right, when V drops immediately, M does not drop immediately because there's no area under that portion of the line. When V drops immediately, V is the slope of N. It's almost like, so let's say this goes from 10 to 2. I was at a slope of 10. Now I'm at a slope of 2. It's this type of discontinuity, just go from one slope to another. So don't drop M straight up and down just because V has dropped straight up and down. If all else fails, you can make a cut just to double check, just to find out, okay, what is my internal V? What is my internal M? All right. So let's do some. I like these. Think about how V or M would change before or after the point in question. So there's some things you can think about.